But I am starting the recorder just so that I don't forget. All right, it is 9 o'clock. I am going to get started. Just a few reminders. I don't think anyone who is currently here really needs to be concerned, but I do want to remind people to check your grades from time to time, just to kind of make sure that everything looks good. And if your grade, especially from the lab, is not, I mean, losing a few points is not a big deal, okay? But as far as the labs are concerned, if somebody's getting like 70% overall, I'll be I'll be concerned because the labs are basically, you can take as much time as you want and you can reattempt as many times as you want as well. But I think I'm preaching to people who really do not need to be concerned. The people whom I think should be concerned are not here, which is ironic. Okay, but it is being recorded. So if those people watch the video, which is also ironic, though those are the also same kind of people who do not watch the video. So yeah. Anyway, today's lab is going to be the familiarization or familiarizing with the TTP toolchain. You cannot see it yet, okay, but I am going to do some demonstration that will help you to answer those questions today, okay? So that means I will be using the toolchain and along the way explaining a few things so that by the time you need to do your homework or do your lab, you will kind of have an idea of, okay, what is this? How do I do this? What does this mean? And so on. So that's going to be the focus of today's lecture. It is more or less, just a demonstration, probably with some concepts introduced, but I really don't think a lot of this is going to be in the second exam by itself. Okay, so we'll go ahead and get started here. All right, so I'm starting Logisim and I'm loading the processor. So today's lab is going to give you the instructions of how you can download all the files related to the processor, how do you get into here, and also how to use the entire tool chain, which I think we touched on Tuesday, right? So we touched on that a little bit on Tuesday, but today we're going to take a kind of like a deeper dive into the tool chain itself and not as much into the processor. The focus on Tuesday was the processor itself. I was, mentioning the two chain, just so that we can see how everything connects. But today's focus is going to be more on the tool chain itself. And I hope most of you are already starting to download or have downloaded the PDF document that is in that is over here. Okay, so there's a PDF, TTP as a PDF. It is just a PDF. It puts the processor circuit, the register bank, and also the ALU circuit all on the same page. You can print it out on a letter size paper. And the idea is you want to highlight the components that are active and also, if you want to track down how a particular instruction works, that gives you a piece of paper where you can actually hand trace, the connection between the components. And I think that's going to be helpful for that purpose. For those of you who do not want to work with physical paper, which I understand, you can also, just use a PDF tool or a tool that can draw stuff on PDF. One of those tools that I have found you to be quite useful, especially if you have a PC that has a touch screen or it is capable of using a stylus, is called Zernal, Xournal, or Zernal Plus Plus. So Zernal Plus Plus is the kind of upgraded version of Zernal, but they both are free. They're open source programs. Um, and you can open up a PDF and then use a stylus to actually write on the PDF itself. So that can be useful for those of you who want to use a PC, or a Mac or a Linux laptop computer to help annotate things. Once you have the PDF. So just a tool that you might find useful. All right. So with that said, we are moving back to talk about the processor. So with the processor, the most important point is in a volume and architecture, both the instructions that dictate how your computer is going to get something done, and also the data that you need to perform the calculation or computation, they're all in this RAM component. Okay, so that means you need to somehow translate a program into the opcode, and then the opcode goes into the RAM component. So that is something that we also talked about on Tuesday. So do we have any questions about the topics that we went over on Tuesday? Because we did went over a lot of stuff on Tuesday. So if you have any questions about any of those topics on Tuesday, I'll be more than happy to clarify or to answer those questions before we move forward in today's class. Any questions? All right. No. Yes, go ahead. Say again. The register bank is a component in the processor that houses the four registers that are software or program addressable. So we are talking about this component here. So when you right click on this component, it will show you what is inside. So the register bank contains registers A, B, C, and D. Now, the names A, B, C, and D are really just an easy way for me to distinguish or to identify the four registers. But these are the four registers that are quote unquote software addressable, which means in the instructions that we specify, such as the subtract instruction that we talked about on Tuesday, we can designate, okay, we want a particular register to provide the minuend. We want another register to provide the subtrahend. And then when the whole calculation is done, we want to store the difference into one of those two registers, usually the first. So that's the job of the register bank, is to house all the registers that you can utilize in instructions. Okay, it provides an external interface to the rest of the circuit as, okay, go back here. So the interface to the register bank, let me go to the poking tool so that I can emphasize on the nodes. So this is the input to update one of the four registers in the register bank. Okay, it has one single input, so you have to use this node here, which is the RISCL, register input select, to specify which register is going to update. It has two outputs, register bank, register output 0 and register output 1. And then these two, depending on how you set up the demultiplexers, can go to various places in the processor. So it's a generalization mechanism so that I can say, hey, I need this register to go here and that register to go over there. And I have the flexibility of not having to fix the pathway between the registers and the other components. I have a way to route the registers to places where they need to go. Does that answer the question? Okay, very good. So a follow-up question is it really necessary to have the register bank as its own component? The answer is no. Okay, but the problem of not doing that is this diagram will get far more complicated than having the register bank as its own component, and the same concept applies to the ALU because the ALU does not really need to be its own component. In other words, I can take this entire circuit here and just paste it into the main circuit here. But that will also make the entire diagram like really busy and difficult to understand. So that's why I created these two subcomponents. One is the register bank, which is here, and then the other one is the ALU, which stands for arithmetic and logic unit, and it is over here because those two are complicated things to begin with. By abstracting those two components into a smaller subcomponent from the view of the processor itself, it makes the processor a little bit easier to track. So is that answering? Okay, excellent. So that's a good question. Any other questions about the things that we talked about on Tuesday? All right. So if the lack of question is because of the lack of time to review the material on Tuesday, I'm gonna have to nag a little bit, okay? It is super important to clear the content of a lecture before the next lecture in this class. I don't know about your other classes, okay? There may be some other classes where it is not important, but in this class, I basically stack concepts on top of basically what we already talked about almost immediately. So that means, the understanding or the thorough understanding of the concepts and ideas of a previous lecture is really, really important. Okay, I just want to emphasize that. All right, so without any additional questions, we are going to take a look at, just generally speaking, how do we write code and, what do we do, to run the program. So we're going to go take a look at, maybe another program. Okay, so this time let me switch back to the to this browser, and we are going to go back to the opcodes table. Okay, so I think I might have talked about in this class and also in the other class, and I think XXYY, this applies to X to Y to XX as well. So anyway, um, I just want to kind of use maybe another instruction to illustrate, the whole process of how do you make a program and get it to run in the processor. So I'm going to try out maybe the bitwise or let's try bitwise AND. Okay, so we're going to try out the bitwise AND operation here. So in this case, column A, once again, identifies the binary opcode, which is basically what you store in RAM. Okay, but you can see that we have 1100. That part is a constant, and then we have x, x, y, y as quote unquote, bits that you have to specify. So we'll ignore x, x, y, y for the time being. The mnemonic, which is column B, specifies that if you want the assembler to figure out the opcode for you, then you have to follow this exact, syntax, which means you have to spell out and, A-N-D, and then you specify a register for the placeholder X. You have to specify a register for the placeholder Y. Okay, so one for X, one for Y. And if you go all the way back up to the beginning, X can be A, B, C, D, because that's how we identify one of the four registers. Y can also be A, B, C, D. So in this case, okay, with the AND instruction, they can be the same. In other words, you can say and B, comma B. Okay, you're performing a bitwise AND of register B with register B. There's a reason why we want to be able to do that. We'll talk about that probably in the next two lectures or so, but right now that is not of importance to us. Column C is what we call the RTL. Does anyone remember what RTL stands for? Because I did specify the name of or the full meaning of RTL, and if you look up column C, it actually tells you what RTL stands for too. What is it? You have to pretend that you're not quote unquote taking a college class. You have to pretend that this is actually at work. Okay, you're at work, and your boss is saying, okay, the RTO of blah 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 is blah blah blah, and you have no idea what your boss is talking about. What are you going to do? You don't tell your boss you don't understand RTL. So what do? You quickly pull out your phone and you look up what is RTL in the context of the conversation. So what is RTL? Or if your boss already said, oh yeah, yeah, RTL, the meaning of RTL is at the beginning or the heading of the column. So you just look it up, right? So so we look it up. Oh, RTL. Oh, I did not actually specify the RTL notation. Interesting. Okay, that's my fault for remembering incorrectly. But I did talk about RTL, the full name of RTL, on Tuesday. So RTL stands for Register Transfer Language. Okay, So very good. I see quite a few people picking up a pencil or typing on a computer right away because that is a real term. It is not a tech term. Okay, there are occasions where I would talk about something and it really is just a tech term. Nobody would refer to those things in the same way. But RTL is not one of those. Okay, it is a industry standard term of describing a particular operation inside a processor. So this means if you want to become a computer engineer, um, RTO is actually kind of important, okay? Because that's how we specify, oh, what does the processor actually do in the process? So that's column C. So in this specific case, the RTL says whatever X and Y are, okay, remember X and Y are placeholders for one of the four registers, we are performing a single ampersand, not a double, okay? Because the difference between a double ampersand and a single ampersand is one is a Boolean operator, the other one is a bitwise operator, okay? So by the lack of you guys taking notes, I'm assuming that you already know what is the difference between a Boolean versus a bitwise operator. Is that assumption correct? Very good. Okay, I like that. Okay, I like the honesty of no, I have no idea what you just said. Okay, because that's exactly what you need to succeed in a college level class. Yes, they are. So a bitwise operator is applying the operation for every single bit position of the operand, as opposed to a Boolean operator, which looks at the entire operand as one single true or false value. Okay, so just that statement by itself, do we understand that statement? Okay, so that's good. Okay, so an example would be helpful. Okay, so let's go ahead and take a look at an example. So the example is going to be, might as well do it this way. This is a really good resource. It's called Online GDB, which is really kind of like Replit, except it doesn't ask you for money. You don't have to sign up for an account. You just go to the website. You can write some C code, run it, and debug your C code. So it's pretty. I like it, because it is pretty handy. So what I'll do is I am just going to use this as an example. In this class, okay, I don't need to use C++. I can use plain C because your plain C is really close to assembly language programming, and that's my personal preference. So what we'll do is we are going to we'll go debug this program. This is like the a useless program, right? I mean, this is what you learn in CISP 360 in the first week. Is just to say hello world, except you probably were using cout instead of printf. So I'm going to debug the program. Okay, so here we have the debugger. Okay, I'm going to pull that up a little bit here. Then you go like, how can this program possibly be useful for illustrating the bitwise AND versus the bitwise or versus the logical AND? So we're going to go put a breakpoint in this program. Okay, putting a breakpoint is basically the same thing as what you would do with VS Code or code blocks. You put your mouse cursor to the left-hand side of the line number, click, and then we'll put a breakpoint over there. If you want to learn GDB commands, you can do so, but if you don't, you can always just press the buttons like that. Okay, so now we are at a breakpoint. In this particular interface, you're at a breakpoint, but you see the green rectangle surrounding a line. Okay, because that means we are about to execute that line, but not yet. Okay, so the execution of the program has now been paused. The debugger is also reflecting that, oh, we are at a breakpoint number one, which is on line 13 of main.c, and we are about to say, to do a printf hello world. So that part is not important. What is important is now you can use print, okay? You can print anything you want, okay? You can print, oh, what is 34 times, 56? It's 1904. Okay, that's so in other words, we have a evaluator, okay, of expressions. The nice thing about GDB is it is, for the most part, not entirely, but for the most part, it will interpret expressions the same way as C or C++. So this means that I don't need to change the program to test out different kinds of expression because I can do that interactively in the debugger. Yes. You cannot declare variables inside the debugger, but in the debugger, it has full access to variables that are already declared in the context of where your breakpoint is. Yep. So it does have some debugging capabilities, but because C and C++ are not scripting languages, so that makes it basically impossible to declare new variables in the debugger. Yep. All right, so what we'll do is now we're going to say, okay, let's print 1 ampersand ampersand 4. Okay, so what do you think is the answer to 1 ampersand ampersand 4? How would you describe the expected output of this print? 1, okay, true, okay, I like that also. Anyone else? True, okay. Now remember, this is C and not C++, okay? The words true, false do not exist in C. So true is basically non-zero and false is just zero. So the only thing I can guarantee is the output is non-zero. I have no idea which one of non-zero. I just know that it's going to be non-zero. So is it going to be one? Yeah, very likely it's just going to be one. But can it be negative 23? Yeah, it's possible. Is it going to be 1067 for no particular reason? Yeah, because those are all non-zeros. So the only thing I can guarantee is it is not going to be zero. Now that difference is actually important, okay? Because a lot of times we would put an integer value in the context of a Boolean, which means you're using an expression that evaluates to an integer, but you're sticking it into the condition of a conditional statement or the condition of a while loop. Okay, which is okay. But at the same time, if you try to evaluate a Boolean expression and then store the result of the Boolean expression into a variable, then you have to think about, okay, do I know what value exactly is going to be stored? Because you don't. Okay, you can only tell whether it's a zero for false or a non-zero for true in C. Okay, so in this case, I think it's just one. Okay, just because that's a kind of like a nice default to have, but there is no promise whatsoever that this has to be one. It can be one, can be negative one, can be 16, can be 1067, can be 20,000, can be negative 16, and so on. Okay, there's just no way to tell for sure what value is going to be returned. Yep, this is still an integer type. It is still an integer type because C does not have a Boolean type. The type called BOOL does not exist in C. It does exist in C++, and in Java, it is very strongly typed. So if you try to use an integer in the context of a Boolean, the compiler would actually complain about it and go like, this is not a warning, this is an error. I will not proceed with compiling any further. But in C++, it will still do the automatic type conversion. So it will take an integer, understanding the integer is in a Boolean context, and then interpret the integer as a Boolean without you having to cast it. In C, it is even worse because it really does not even have a Boolean type to begin with. All right. So what I have just said in the past 5, 10 minutes or so are not things that are immediately going to impact you in this class, but it will impact you if you continue to write programs in C and C++ and also Java. Okay, so sometimes I kind of bring in the context of some other classes into this class, but it's like it still might be useful, in your other classes. Okay, so what we'll do now is to say, what about just one single ampersand? It is a bitwise and then the result is like, what? What is going on here? Okay, wait. Okay, let me try something else. What is one logical AND with one? It is one. What is one bitwise AND with one? Seems to work. So the reason why this is the case is because the bitwise AND of 1 and 4 is going to look like this. Okay, so let me use, I think I'm going to use Joplin because, Joplin is just kind of a nice interface. Okay, so we'll go back and switch to CISP 310 and a new note, and we'll call it under today's date. So this today is one like so. All right. So now we'll take a look at the bitwise AND operation. This is what we call a text block, so I can use fixed size font. So what is one as we'll just give it 4 bits, okay? What is one as a 4-bit number? That's an easy one. Yep, it would be 0, 0, 0, 1. Okay. When you perform a bitwise AND, what is 4, by the way? 0, 1, 0, 0, because 2 to the power of 2 is 4. Okay, so that's why it is 0, 1, 0, 0. So with a bitwise AND, as the name implies, it is performing an AND on each bit position. So the cursor is currently on bit position 0, right? So what it's going to do is it's going to take bit 0. Okay, let's name the first row X and the second row Y, just so it's easy to refer to those two rows. Okay, so here's X, here's Y. So this is X0 and Y0. Okay, so it is basically 1 and 0. And what is 1 and 0? It's a 0. Okay, so we put a 0 over here. This is X1 and Y1, and that would be 0. This is X2 and Y2, another 0. X3 and Y3, also a 0. So that explains why one bitwise AND with Y is a 0, as opposed to, well, why is it not true? Because we are not looking at 0001 and 0100 as integers anymore. Okay, each one is broken up into individual bit positions, and then the bitwise AND is specifying, let's do an AND operation on a bit by bit, position by position manner. Do we have any questions about this? No? Okay. So let me see how quickly you guys can do base conversion. Okay, so yeah, it happens like this. If you leave it for too long, it's gonna disconnect and want you to restart the whole debug session, but that's okay. It's not a big deal. All right. So let's see what you guys how quickly you can do something like this. So we are now saying, what about D? Okay, hexadecimal D, bitwise AND with um 2. So this requires you to look up the table, okay, which I have given you, and look up what is hexadecimal D as a binary number, as a 4-bit binary number, and then what is 2 also as a binary 4-bit number, and then you perform the bitwise AND operation. So what is the result of this? It's also 0. Exactly. So the reason why this is 0, but I think most of you already know why, even though you may not be doing the base conversion as quickly as I could, but I think you already know why that is the case. B is, excuse me, D is 13. 13 is 1, 8, 1, 4, no 2, and a 1. That is D in hexadecimal. And then we are doing a bitwise AND with 2. So that's no 8, no 4, 1, 2, and no 1. This is our Y. And you can also see, no column has 2 ones at the same time. So that means, pretty quickly, I can now say they're all zeros. And that's why the bitwise AND between D and 2 in hexadecimal is just a 0. Okay? So the problem with bitwise AND is in most cases, if you have just a regular Boolean value on the left-hand side and a regular Boolean value on the right-hand side, they are typically zeros and ones. And if they're both zeros and ones, then bitwise AND versus logical AND would not make a difference. So that means if you have a genuine typo in your program, you actually intended to use double ampersand, but you forgot to use double ampersand and you only put in one single ampersand, most of the time the program would actually work. But the moment you change the compiler, it may not work anymore because different compilers can use a different internal standard that is still conforming to the language specification itself. Those are some of the worst kind of bugs because the program clearly worked with my compiler, but when your professor compiles the program and run it, it doesn't work. You cannot go to the professor and go like, but it worked when I ran it, I deserve all the points. No, that is a flawed argument. It is not a bug in the compiler. The two compilers chose to interpret the same requirement in a different way, but they are both compliant to the language specification. That's the thing. All right. So just minor little points like this. Okay. So now we can go back to my original plan, which is to illustrate how to get this program to assemble. All right. So now we go to the assembler. And to specify a program, you always want to go to the source tab, okay, or the source sheet. So for people in the back, you may or may not be able to see this, tab here says your source. So in the source tab, you typically want to clear out the entire column A, and I would just highlight the entire column A and press the delete key on the keyboard to clear the whole thing. And now you can specify your code. So in this case, I'm just going to specify and let's pick two different registers. We'll try B and C this time. Okay. And then we'll have a halt instruction. Okay. So what do you think the halt instruction does when the program executes? Yes, exactly. It halts. Okay. So the question now is, but why do we need a halt instruction? What if we don't have a halt instruction? And by the way, double slash is also serving the purpose of commenting, just like in C++. Okay, I chose that standard just because most people know how to use double slash. So the question is, what if I don't specify a halt? Okay, so you can also see that there are no errors on column B, which means everything is actually good. You don't have to read the entire formula here because that's just my uh, Google Sheets magic, to report errors when there is one. Okay, so this is your program in mnemonics. The job of the assembler is to do the whole thing, the tedious thing of looking up the opcode table, go to the right row and specify and look up, okay, what two registers are we using? We're using register B and register C. So that means, X is B, Y is C. And then you have to look up register B means, we have to use 0, 1. Register C means we have to use 1, 0. So that means the XX is going to be 0, 1, the YY is going to be 1, 0. So that means the whole opcode is going to be 11000110, which in hexadecimal is, I'm just trying to see if you guys are tracking and following all the zeros and ones. Is a C, okay? 1100 is a C. And then the other one is 0110. So what digit does it correspond to? 6, very good. So C6 is the hexadecimal representation of the binary pattern that we want to output from the assembler. So now we can double check to see that is the case. So in order to see the output of this whole thing, there are two tabs that can be used. One is a little bit more informed, but it might give you information that you don't really need right away. The other one just gives you the raw information. So the Assemble tab gives you a little bit more than what you really need. So it tells you that at location 00, we have the content of C6, okay, which is consistent with our own hand assemble method. And then the RAM file does not even give you the address. It assumes that we are starting at location 0 and we just have a single byte of C6 in this case. Do we have any questions about the respective roles or responsibilities of the three tabs that we have talked about? The source tab is where you enter the program. The assemble tab is you can actually see which line of your source code assembles to what byte orders. And then the RAM file is the actual file that you need to download in order to load it into the RAM component of the processor. Do we have any questions about those three tabs? If the lab involves, this kind of activity, do you think you remember or you have the notes to remind you, oh, okay, programs go into the source tab, and then the RAM file tab is where I actually download the file to put it into RAM. Okay. All right. I can see people are starting to write down something, okay, or at least make a mental note. Great. And obviously, for people who did not do that, and I'm keeping an eye on the whole class right now, I will give those people a really hard time. And that's actually my job too. I have to give myself a new job description. Make sure people have incentive to pay attention in class. Yeah, there you go. Alrighty. So moving on. Now we want to load this program into the RAM component of the processor. So we switch to Logisim. Okay, right there. Go to the RAM component, and this is how we load a file that you download. Oh, I forgot. I have not downloaded the file yet. Okay, so when you are in the RAM file tab, okay, you have to be in the RAM file tab first. Go to File, and then go click on Download, and you can use either one. You can use CSV, which is comma separated value, or tab separated value. They both will work, okay? But as a convention for myself, I choose to use CSV for this purpose, but you can choose either one. So you click on this, okay, and we save the file. This has no particular value, so I'm just going to save it as test.csv, replace the file that I already have in the system, and now I can switch back to Logisim. So in Logisim, you right click on the RAM component, and then you select Load Image. So now it will ask you, where is the CSV or TSV file? I can type the entire path because it's relatively easy. So it's just test.csv in my temp folder. If you're using a PC, it is probably going to be in your downloads folder. Okay, so depending on what operating system you're using, and also the default settings of your browser, it can be at a certain different place. Okay, so right here, press the enter key and you can see, oh, great, C6 is now in RAM. I have successfully loaded the whole program into RAM. We good so far? So what we'll do next is to just take a look at the execution of this instruction, but in, how do you call those things? It's in, is it called fast motion? Quick motion? Huh? Not slow. I want to kind of make it faster, like accelerated motion. There's a term for those things in movies. Bullet time. It's making things go faster, not slower. It's the opposite of the matrix effect. The term is right at the tip of my tongue, and I cannot say it. That's a sign of aging, by the way. You guys don't have to worry about it for a while. All right. But in order to do that, let's put something into register B and register C just so that it is a little bit more interesting. So I'm gonna put 4C over here, and then we'll put C4 over here. Okay, so they're symmetric. Okay. All right. So now we can go ahead and execute a program, which is repeating things that we have already talked about on Tuesday. So if this sequence does not remind you of things that we have already talked about, that means you might need to go back to the recording on Tuesday and watch it again. Okay, because I'm basically using exactly the same sequence, except I'm going through it a little bit faster than on Tuesday. So first thing first, okay, when the microcode pointer is at location 000 and I'm having a rising edge, Control T right now, it is called the fetch phase of execution instruction, of instruction execution. And the only thing it's going to do is to load the opcode that is pointed to by the program counter, which is PC, into the register called instruction register. So that's fetch, okay? So we talked about this on Monday, okay? So if you're not remembering that, you might need to watch it again. So Control T, we can see how C6 is now loaded into the instruction register. That's called the fetch phase of instruction execution. The next one is going to be a falling edge. The falling edge only affects the microcode pointer. In this case, it's going to only increment the microcode pointer to 001, Control T, like that. So you can see how the ROM instead of location 000 being addressed, now it is addressing location 001, which means this content is being presented to the D port of this ROM and therefore controlling all the multiplexers, demultiplexers, which register is supposed to be enabled, blah blah blah. Okay, so this step is just going to auto increment the program counter itself. So the program counter will increment from 00 to 01. And the idea, the purpose behind this is we just fetched the opcode from location 00. There's no reason why the program counter should continue to point to location 00. So this is the processor preparing for the next fetch operation. Okay, so Control T, as expected. Now, this next transition is also important. The microcode pointer is at location 001. We are going to experience a falling edge. So do you remember the name of this particular transition in the cycle of instruction execution? It starts with a D. Decode, very good. Okay, so this is the decode step of instruction execution. So the decode phase is going to take C6 in this case and make it combine that with the least significant hexadecimal digit of 0 so that the microcode pointer becomes C60. Control T. Okay, that's exactly what is happening here. So this content here, sometimes I call it a slice, other times I call it a microcode, but they mean exactly the same thing. So this particular microcode is outputting a certain pattern so that the registers will be enabled or to be updated. The ALU will be activated and the correct component in the ALU would also be routed to, at the same time. So this is how we get the actual AND operation done. And I'm not going to go through the whole analysis because otherwise it would just be repeating what we already did on Tuesday. So instead of doing that, I'm just going to point out the obvious. We go to the ALU, and then we go to the component that does all the actual bitwise AND operation, which is our AND gate here. We would expect C4 to be here, or 4C over here, and then C4 to be over here to basically reflect the content of register B and register C. Okay, so now the question is, what do you think is the output? Based on what we have just learned about bitwise AND, what do you think is the output? C, by the way, is 12 in decimal. So we are doing a bitwise AND between 12 in decimal and 4 in decimal. But you cannot do bitwise AND operations in decimal. You can only do that in binary. So now you have to think about, how do I express 12 as a sum of powers of 2, and how do I express 4 as a sum of powers of 2? If you have to spend more than 10 seconds to think about it, you might need to kind of sharpen your math skill a little bit, because 12 as a sum of powers of 2 is 8 plus 4. 4 itself is a power of 2. So now we are looking at 1100 bitwise AND with 0100. So the result should be 01 which is a 4. Okay, let's double check. It's a 4 4 because I'm talking about the most significant 4 digits has this situation. The least significant 4 digits also has the same situation. So it is a 4 4 in this case in hexadecimal. All right. So now we can go back out, okay, without looking at all the multiplexers and demultiplexers, which is exceptionally tedious. We go back to the register bank and say, we are expecting register B to update to 4 4. Is it really the case? Yep, that really is the case. So Control T, the instruction has just got its job done, right? So now the question is, but Tech, you never really talked about what happens after an instruction executes successfully. Okay, so we're going to continue with that. So this part is new compared to what we did on Tuesday. So now we are going to have a falling edge. So a falling edge only affects the microcode pointer. And in this case, because the multiplexer has a select of 1, so that means we are only going to increment the microcode pointer. Except when I type Control T, it is not going to look like that. Okay. The reason why it's not going to look like that has to do with in the ROM, what is the next location? So we'll go into the ROM here. And the way you read the ROM content, okay, I need to move this window into the view that you can see. Give me a second. All right. Oh, there we go. All right, so we want to go to location C60. Okay, so we go to C60. So this little exercise here is telling you that the leftmost column where the numbers are in italic, that is the address, okay? That is the address of the leftmost item on the row. So this is the um, the content at location C60, and the next one is 2 followed by a bunch of zeros. Is that okay? So by incrementing the microcode pointer, which connects to the A port of the ROM, that means, oh, okay, this is going to specify the bit pattern coming out of the D port. Okay, but what does that bit pattern look like? You go like a bunch of zeros, and it has a single one. Okay, so we want to find the bit position of the 1 in this case. So we have how many hexadecimal zeros? 1, 2, 3, 4, 5, 6. So there are 6 hexadecimal zeros. Each hexadecimal zero means 4 binary zeros. So that means we have 24 binary zeros. But after that, we have no 1 and a single 2 over here. So that means we have a total of 25 zeros in binary, and then finally a 1 for bit 25. Okay, are we still doing okay so far? Okay, with the bit counting. So now when we look at the output of this thing here, it means, oh, okay, so that means if I do a Control T, that means the next output from the ROM will only light up this particular wire. Everything else is going to be a 0. Does that make sense? Because the wire that I'm highlighting right now is bit 25 of the output of ROM. Okay, so where is that going? It's going to an OR gate. So if at least one input of the OR gate is a 1, what is the output of the OR gate? It's also going to be a 1. So where is that 1 going to in the next, after I do a Control C? Tell me what is this port of the microcode pointer. It has a label of 0. What does it do? So that's one of the things you can look up, okay? But I'm going to tell you, okay? This is called the clear port of a register. If that port is a 1, the register will be reset to 0. In this case, 0, 0, 0. So that's exactly what is going to happen because we would expect the microcode pointer to increment to C61, which it does. But at almost exactly the same time, with a very short delay, it will reset itself back to 0, 0, 0. Okay, so let's go ahead and do this. Control T, and you can focus on the microcode pointer here because you will not visually see it to become C61, even though it does get to that location for a very short amount of time. All you can see is it will be reset to 0, like that. Okay, so at what stage of instruction execution are we at? The microcode pointer is 000. The clock is low. We are about to experience a rising edge. Exactly. We are now back to the fetch phase of instruction execution. So now the question is, where am I getting that instruction? The entire program has only one single byte. So where is it going to get the next byte? Well, unfortunately, RAM does not have a boundary of where the program ends. So that means whatever the program counter is saying, that's where I'm going to get the next opcode. Is that okay? So the next opcode is at location 01 in RAM, which has the content of 00. And guess whose opcode is 00? No op. It's not halt. We wish it was halt, but it's no op. Okay? So, okay. So if you are already thinking, it's like, wait, if we decode 00, it just becomes 000, which means the opcode 00 is going to send the processor back to the fetch cycle again. So if you're already making that association, congratulations, you are 100% correct about that. And that is the whole reason why the no op instruction does not do a single thing, because the decode of the no op brings the processor back to the fetch phase of instruction execution. Okay, so you go like, okay, you just use a lot of words that I cannot make connections with. So let's go ahead and demonstrate it. Okay. So now we go back to the controller part of the processor. This whole part here is called the controller of the processor, but it's not super duper important. So Control T, okay. So without any, not surprisingly, we are basically fetching the content of location 01 into the instruction register, which is 00. Control T again, increment the microcode pointer. Okay, so you can observe the microcode pointer here getting incremented. No big deal. The next one is going to increment the program counter. So look at the program counter over here. It should increment to 02. Okay, not a big surprise. So now it's the decode, right? It is decode time because the microcode pointer is 001, and we are now going to have a falling edge. Okay, those two are the conditions of, okay, are we in the decode phase? Yes, we are in the decode phase. So the decode phase is now going to take the 00 from the instruction register to make up bit 4 to bit 11 of the actual content that we'll put into the microcode pointer. The least significant 4 bits are going to be 0 anyway. So now this wire is going to specify 000 because we are decoding 00 as an opcode. Okay, so let's check it out. All right, we do have 000 here. So that means the falling edge, okay, right now, which is the decode, is going to send the controller, which is the lower portion here of the processor, back to the fetch phase of instruction execution without doing anything really useful. Is that okay? The only side effect of the no op instruction is the program counter gets incremented. That's it. It does not perform any calculation, does not update any other registers. Question? It is fine until it is not. Okay, so I'll explain why when it is not okay. Okay, so we do a control T and okay, we are back to the fetch cycle, except now the program counter is at 02, which means we're now ready to execute the second 00 in RAM, which is at location 02. Okay, so it'll keep doing this until it reaches location FF or 255. And then what do you think it's going to do? It won't break. Because what happens when you add 1 to FF in hexadecimal? What happens when you add 1 to 1111 Yes, it just wraps around to 0. So that means this entire program is going to get to the end. It will execute a no instruction, which is harmless, all the way to the end of the address space in RAM, and then wrap around and start all over again, which may not be what you want. So we are going to visualize that. Okay, so we will go ahead and visualize that by focusing on the RAM. The nice thing is the RAM always show you which location is being addressed, so we can actually see that thing kind of going around, and then suddenly it just goes back to 0. So we go to simulate, double check the frequency is reasonable, 128 hertz is fine, and then we enable the tick. So this way I don't have to keep clicking on my keyboard. Okay, are we ready? The nice thing is this is getting recorded, so if you guys want to go back and capture the moment that it wraps around to 0, you can do so. All right, there we go. Did you see it? Yep. So the program does not stop, which can be problematic, right? So how do we fix this problem? Let me stop the ticking first, and then we will try to address the question. So, that's why we need a halt instruction to explicitly tell the processor, do not execute past this point. That's the job of the halt instruction. All right, so what we'll do is now we go back to the program, okay? Go back to the assembler, okay, there you go. And we'll change the source code to just a little bit by uncommenting the halt instruction. So we just kind of put the halt instruction back in, and then we go to the RAM file, and then we just go to File, go to Download, go to CSV. I mean, this is a really simple program. I really did not have to do that, but I'm doing it again just to illustrate the sequence again so that no one is going to ask me that question when you're doing your lab. All right, so it's all done. Switch back to LogiSim, right-click on the RAM component, click on Load Image, and now we go back to the temp folder, re-specify test.csv, click Open, and it's already there. It's just that we cannot see it, okay? All right, so this is also a good time to introduce, how do we reset the processor? You can type a Control R if you want to. The problem with the Control R is it also clears the RAM component. So my way of doing this is to make sure the clock is at a low state, so you can always force it back into a low state by clicking it. And then you click the reset button here. Instead of doing a Control R, you just hit this reset button. And what that will do is it will basically reset everything except the RAM component maintains its content. All right, so this time I'm going to kind of speed through the execution of the AND instruction so that we can just kind of focus on the halt instruction. So I can do some counting on my head of how many control T's I need to move past the first instruction. First control T is a fetch. Second control T increments the microcode pointer. Third control T auto increments the program counter. The fourth control T decodes. The fifth control T is going to execute the actual AND instruction. The sixth control T is going to proceed to the next instruction. So I need 6 control T's to move on to the 0, 1 or the halt instruction. Is that okay? Yep. It would be 3 cycles because there are 6 transitions. Yep. Because one rising edge combined with one falling edge is 1 cycle. So we have 6 edges, which means we only have 3 cycles. Yep. So the idea is if you can name all those operations, the 6 control T's or the 6 edges, as quickly as I was able to do it, then you are mastering the execution cycle of this particular processor. Okay, um, which may or may not be important. Okay, but I think it's a good indication that you're getting a handle on how the processor works. So from that perspective, I think it's a good thing. All right, so we're just going to count six. Okay, one, two, three, four, five, six. Oh, okay. So now we are at the fetch cycle or the fetch phase of executing the instruction corresponding to location 01 of RAM, which also turns out to have the content of 01. So we'll go ahead and go through the fetch, okay, control T, and then the falling edge to increment the microcode pointer like so. And then the next rising edge is incrementing the program counter like so. And now we're going to decode it. Another control T. All right, so now the instruction is decoded. So we are going to be curious of, oh, which location of ROM is it going to address? Well, is that surprising to you that we decode the whole thing to 010, with the microcode pointer? If the opcode is 01, the decode is going to change the microcode pointer to 010. It's just appending a 0 on the right-hand side. So that part should not be surprising. So what is also not surprising is, oh, we just have a whole bunch of zeros over here. That is correct. So what do you think happens with when I type Control T again, which is going to be a rising edge? Okay, so if I type Control T again, I know I'm going to have a rising edge because the clock is low at this point, right? But the only register that is sensitive to a falling edge is the microcode pointer, which means everything is sensitive to a rising edge, right? So you would think, okay, this is a rising edge, so something is going to change, except for one thing. In order for another register or RAM to change, it has to be selected or enabled, which means something has to be a 1 coming out of the ROM. Does that make sense? But do we see any ones coming out of the ROM? They're all inactive. They're all disabled or not selected, depending on how you want to name it. Same thing. So that means the rising edge is going to do absolutely nothing because none of the registers is enabled. The RAM itself is not selected, so nothing is going to respond to the rising edge of the clock. Okay, they're all falling asleep right now. Okay, so Control T, okay, right here. Nothing happens. You can double check if you want to. Nothing happens to the entire processor. So now we have a falling edge again. So what is the condition of this falling edge? The condition of this falling edge is um, the microcode pointer looks like this. The more important part is what about this multiplexer? This multiplexer is the the select of the multiplexer feeding to the microcode pointer. This select wire over here is also coming out of the ROM and it is a 0. So that means from the multiplexer's perspective, it's going to take input 0 to update the microcode pointer, which is also the same thing as what we do when we decode. In other words, it is decoding the instruction of the instruction register again. Did we change the instruction register? Nope. So that means it is re-decoding 01, which leads to the microcode pointer to stay the same as 010. And now we are in quote unquote an infinite loop that does not do a single thing. Am I doing okay so far with that explanation? Because we are decoding again. Why are we decoding again? Because the multiplexer has a select of 0, which means it's taking input 0 of the multiplexer to update the microcode pointer. But input 0 of the multiplexer is coming from the instruction register, which has not changed. So we are basically re-decoding 01 as an instruction into the microcode pointer, which is already 010, which means we are not going to change anything. So now I can control T all day long, okay, and nothing happens to the entire processor. So that is how the halt instruction works in this processor. Do we have any questions about this? You mean continuing past a halt instruction? I cannot think of a case like that. Okay, I think the halt instruction does something like this across all architectures. So the TTP is not the only one that behaves like this. If you look at a more modern processor, especially one that goes into mobile devices like your fitness watch or your cell phones and whatnot, the halt instruction would also can optionally put the processor into a low energy state, which means the clock actually either is really slow or it stops entirely. So you go like, okay, so what is that going to be? How is that going to be helpful, right? So if my fitness watch processor is falling asleep, okay, that means it's not going to respond to anything. Well, that is not entirely true, okay? Because a timer can operate independently to the main processor, to your program. And the timer can give you a interrupt, okay? It's also a different concept, but we'll talk about it later in the semester. So it can cause an interrupt, which would wake up the processor. The processor will then go to the ISR or interrupt surface routine to do whatever it needs to do, such as reading the LED and also the photo sensor so that it can kind of check your pulse and whatnot. And then it will go back to sleep. So that means most of the time, your fitness watch processor is actually not actively doing anything. It's waiting for the timer to wake it up and go like, okay, it's time to take another measurement of what the LED or what is the reflection coming from your flash, so they can see it can differentiate whether there's a pulse or not. Yeah, but even in that case, the processor is still stuck at the halt instruction. Yep. Alrighty. At least with that thread. I have to be careful with that because you can have multi-threading. So if your processor is multi-threading, then each thread can have a different idea of what it should do. Yep. Alrighty. So we have about another 15 minutes or so. So now we're going to we'll go take a look at some program that you probably do not understand what it's going to do, but there's a question that relates to this kind of interpretation. So um, I'll try my best to explain it, okay? But at the same time, I will also be a little bit difficult for people who ask questions related to this one because I'm talking about it. Okay, so there are different types of instructions. There's no op, there's and, BC, and there's a LDI instruction. Okay, you don't have to be concerned about what the LDI instruction does at this point. I'm just going to throw it in here. There's a JMPI instruction to label L1, and since L1 is not defined, it's going to complain about it. It's okay, not a problem. And then we can define the label L1 over here. So now the program does assemble, okay? You don't even want to run this program. It has a tight loop. Well, actually, it doesn't have a tight loop, but it's not a good program to run. The question is, let's take a look at the assemble tab. So if I go to the assemble tab and I ask you, um, what is at location 03, what would be your answer? So now you have to understand what is column W, what is column X, and what is column Y. Column W is the address in hexadecimal. So this is basically saying at location 01 in memory, we are supposed to see the content of 86. Is that okay? At location 04, we're supposed to see the content of 40 and so on. So if I'm asking you, where is this 07 located? What would be your answer? 0, it will be 02? Well, not exactly. The 67 or the 6C is at location 02 because remember, this address is the address of a byte. This is already a byte. So 07 cannot be at the same location as 6C because they are two different bytes. So if 6C is at location 02, where is this byte? And why do we skip a certain location when we move on to the next row? So where do we find 07? What is the address of 07? 03. Very good. Yep. So that's the reason why this is the case is because some instructions take 2 bytes. So in this case, the LDI instruction will take 2 bytes. This address is the address of the first byte of that instruction, which is the byte that contains the 6C. The second byte does not have its own address declared because it is sequential to the first byte. Are we doing okay so far with this? Okay. So you can say, okay, but I'm not really sure. I think I understand, but I'm not really sure that my understanding is correct. There are two ways you can verify your understanding. Okay. One way is to look at the RAM file because the RAM file does not spell out the addresses. It is just a sequence of bytes starting at location 00. So if you do your own counting and you ask what is at location 03, then you go like, this is location 00, location 01, 02. This is at location 03. So this is one way to do it. But if you're not convinced, even using this method, you can also just go ahead and download the CSV, and I'll call this one test1.csv. Then you can always go back to the processor, go to the RAM. Okay, in fact, I'm doing Control R to reset the whole processor. Go to the RAM component, right click, load the image that we just downloaded, which is test1.csv in this case. And now you can double check and go like, okay, where is this 07? You can also do the counting again. The left-hand side, these numbers are the addresses of the leftmost byte on the row. So that means the highlighted 00 is the content at location 00, 86 is at location 01, 6C is at location 02, and this 07 is at location 03. So are we okay with that concept? How we count the bytes? We good? All right. So I think with that, you should have everything that you need to do the homework assignment. So we are going to use the rest of the time to talk about RISC, RISC, versus CISC, which is CISC. Okay. So if I were to ask you, what is RISC and what is CISC, what would you do? Yep. hmm Yep. Well, now that you guys all have access to Gemini, did you know that you have access to Gemini through the school account? You did not. Okay. So the California Community College Chancellor's Office, CCCCO, has made a deal with Google, and the Chancellor's Office has paid for 3 years of contract with Google to offer all students, staff, faculty, and administrators basically free access to Google Gemini and also Google Notebook LM. So if you sign in through your WID at apps.losrios.edu, you now have access to Gemini, okay, which is kind of cool. But I do have to give you a warning, okay, before you start to research things like how do I hack Canvas so I can enter a good grade for myself. You might want to know that you cannot delete your conversations. Yes. It is, but this is a subscription level kind of service, so you can actually use basically unlimited questions. So that's kind of cool because I think the free version does not. It gives you some kind of cap of how many questions you can ask or how many tokens you can use per hour or whatever rate. This one does not have that limitation. But remember, you cannot delete your conversations. Okay, so if you use this account and you ask something that may come back and trouble and bother you in the future, you cannot delete those conversations. So do not do anything suspicious when you're using this account. What you do with your own account is up to you, but don't do it with this one. So, but the nice thing is now you have access to Gemini, so you can really ask it what is RISC, RISC versus CISC. Now, I intentionally did not give it a lot of context just to test how well Gemini can look at just the terms and decide, oh, okay, this is a computer architecture issue. So let's go ahead and press the enter key and see what happens. I don't even use the capitalization and the proper grammar, and it was able to find it. Okay. So what is the big difference? The big difference is obvious when you get to the opcode table. So when you get to the opcode table, let me ask you how many instructions are there with the TTP. So the starting point is here, which is on row 7, and then the ending point is here on row 33. There might be some instructions that are not even implemented anymore in between, but let's just say it is 7 to 33. So 33 minus 7 is 26. 26 plus 1 is 27. So there are 27 instructions for TTP. Okay, and you guys might think 27, that's a pretty big number. But many of those instructions, like no op or halt, are fairly like you don't need to really. I mean, there's not much to say about those instructions, right? So now we can also go back to Gemini, and then we ask, what about a typical Cisp architecture? Okay, the AMD 64 is a typical Cisp architecture. You can confirm that, right? You can say, is the AMD 64 architecture a Cisp? Okay, and it would probably give you a longer answer, but ultimately the answer is yes. Okay. La, 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 la. Okay, it's fundamentally a CISC architecture, blah, blah, blah. So now the question is, how many instructions do we have with the AMD 64 instruction set? Okay, so we'll ask that question. So we ask how many instructions, or I think the better way to say is how many, yeah, instructions are in the AMD 64 instruction set. You're not gonna like the answer. And then you appreciate that I do not use the AMD 64 architecture in this class. Around 1000 to 1500. So do you want to deal with 27 instructions, including no op and halt, or do you want to deal with more than 1000 instructions? So there you go. Okay, so the complex instruction set computer has more instructions. And the characteristic, if you go back to the earlier description, the characteristic between the differences of the characteristics between the two architectures is with a CISC architecture, each instruction can do more things than a single instruction with a RISC architecture. So in other words, you can say, oh, a complex instruction set computer instruction, a CISC instruction, is basically several RISC instructions rolled into one. Okay, that's one way to look at it. Okay, so most people would think, oh, that means CISC is better. Okay, RISC is, it needs more instructions to get the same thing done. That is actually true. Okay, it is actually true that it will take multiple RISC instructions to get one CISC instruction done. So it would seem like, the balance is going to tip to the CISC side and not so much onto the RISC side. So what most people do not understand is what is going to limit how much processing power you can pack in the data center. So we are talking about huge structures, okay, with rows and rows and racks of computers. So what do you think is the limit of, oh, we cannot pack more processing power because of this? Okay, what is that? Cooling, exactly, is the thermal output of computational hardware. Okay, so as it turns out, CISC architecture requires more energy per computation. So if you think about calculus, I know you guys are not really fond of calculus, but we'll think about calculus just because you're not fond of it. So if you think about calculus and you say, okay, I need to numerically calculate the area under this curve, okay? It will take a CISC architecture more energy compared to a RISC architecture to get that computation done. Now, why is that? The reason is simple. With a CISC architecture, in order to implement the 1500 instruction set, the die size is going to be huge. Okay, it just needs a lot more transistors, a lot more gates to get a job done because it needs to know how to do every single one of those 1500 instructions. Okay, On the other hand, a RISC architecture has a tiny little die size because it only has like a small number of instructions to implement. So it can be done using less transistors, less silicon. So just because the die size difference, we already kind of get an idea of why Cisc is less energy efficient because you have a lot more transistors to power up. Even though most are not really doing anything, they're still powered up. They're still outputting thermal, they still have a thermal output. In other words, they're still warming up the surrounding. So that is the reason why Cisc is not advantageous when you want to use the least amount of energy to compute, to do the most computation. Okay, yeah, go ahead. That is not true either, but with risk, you can parallelize a lot more. In other words, in order to have the same thermal output, now you can say, oh, I can have this many RISC cores all working at the same time, and it would have about the same thermal output as the one single Cisc processor. That is how RISC is going to win the game, is by saying, oh, I can have a whole bunch of processor cores all working at the same time, and it is still not using more power than a single core from a Cisc. So that is the main advantage. So, but this is kind of interesting. This is also why we are tipping everything to the risk side. So that so only one question remains is how come the PCs are still using the AMD 64 architecture? The answer comes in yes, yes, but who built that? Which company? So which company is responsible for the continual use of CISC architecture when the RISC architecture has every single advantage? Microsoft. It's because Microsoft does not have well, this is just my speculation, but I think it makes sense. I think Microsoft does not have the internal structure to retarget all their software like Windows, Office, and all their server stuff to a different architecture, not reliably and not efficiently. Because if you look at some other operating systems like Apple, but Apple is kind of mono culture also. Once they switch everything to the same architecture. But if you look at Debian, okay, so we'll go ahead and take a look at architectures supported by Debian. So Debian is a flavor of Linux, okay? Um, all right, so these are the main ones. Just look at that list. I will bet you do not even know many of these architectures. Okay, so you would ask. So this really begs the question of Debian is open sourced, Linux is open sourced, which means the people who do all this work, they're not directly getting paid. Okay, their employer may be paying them to do some work, but they're not directly getting paid by Debian or the Linux Foundation. Okay, a lot of times we have grad students porting Linux to you know basically theoretical architecture that does not even have a silicon version. Everything is in simulation. Okay, so the question is, how come people can do this with Linux and Microsoft as a what valuing as what $3 trillion now cannot do the same? Because Linux is open source, yes, that is true, but I think it has to do with how much they value the portability from one architecture to another architecture. Microsoft actually had tried multiple times to port Windows and all the applications to different architectures, and every single time they would do it for about a year or so, and then they back off because they don't want to spend the extra time to have to maintain multiple architectures at the same time. Anyway, just a little tidbit of CISC versus RISC, and we really have no reason to use CISC anymore, but because of software that are already developed, and also we don't want to waste the effort to have to recompile everything, risking the recompilation may introduce errors. that is the reason why we still maintain certain CISC architectures, because otherwise we would have moved on to RISC architectures for everything a long time ago. All right, so that's it for today's lecture, and I will open up the lab so that you guys can get started with it. So the lab is called um, Familiarizing with the TTP toolchain. It is now visible, and then the access code is TTPASM. TTPASM, all uppercase. I'll double check that you guys can get in, and then I'll go get some water to drink. Yep. Oh, not showing up? Hmm? You find it? Yeah, you have to refresh it because I think when I enabled it, there you go. Okay, very good. All right. So I am going to stop the recorder, get it uploaded, and then I will